This paper resolves the past complexity of approximating maximum matchings in dynamic graph streams via semistreaming algorithms. The authors present a randomized sketching-based semistreaming algorithm for O(1) approximation of maximum matching in dynamic streams using O log n passes, exponentially improving upon previous O log n pass algorithms. This algorithm is based on a model-independent reduction from matching to maximum independent set (MIS), and utilizes a random-order greedy approach. The authors also establish a lower bound of omega log n passes for any semistreaming algorithm for O(1) approximation of maximum matching in dynamic streams, settling a long-standing open question. This lower bound is based on the hierarchical embedding technique and uses information-theoretic arguments to address challenges in applying hierarchical embeddings for approximate matchings. The paper's contributions include settling the past complexity of approximating maximum matchings in dynamic graph streams, presenting a randomized sketching-based semistreaming algorithm, and proving a lower bound of omega log n passes. The techniques used include a model-independent reduction from matching to MIS, a random-order greedy algorithm for matching, and information-theoretic arguments for the lower bound. The dynamic graph streaming model involves processing a graph with vertices V and edges E, defined by a sequence of insertions and deletions in a stream sigma of length n. The goal is to make one or a few passes over the stream, using limited memory, and compute the answer to a given problem on the graph G at the end of the last pass. The authors present two main results, including a randomized O log n pass O(1) approximation semistreaming algorithm and a lower bound of omega log n passes for any randomized semistreaming algorithm. The paper's results have implications for the design of efficient algorithms for dynamic graph streams and provide a better understanding of the limitations of semistreaming algorithms for this problem. The techniques and results can be applied to other problems in dynamic graph streams and have the potential to lead to new breakthroughs in this area. A novel approach to dynamic graph streaming algorithms has been developed, leveraging graph sketching to achieve an O(1) approximate matching in O log n rounds with n size sketches. This result implies a massively parallel computation (MPC) algorithm for approximating matchings in O log n rounds, using machines of n memory and only n working memory. The approach utilizes the O log n pass semistreaming algorithm for maximal independent sets (MIS) as a subroutine and draws inspiration from recent work relating MIS to the vertex cover problem. The algorithm's first main technical ingredient is a model-independent reduction from O(1) approximate fractional matchings to the randomized greedy MIS algorithm, inspired by the work of Veld 24. The second main technical ingredient is a partial implementation of this reduction in O log n passes of dynamic streams, relying on the semistreaming implementation of the randomized greedy MIS in O log n passes by ACG plus 1.5. The lower bound follows the hierarchical embedding technique of AKNS24, creating hard instances for PPASS streaming algorithms by embedding many p-1 pass hard instances in a single graph G. The approach uses combinatorial construction of hard instances with edge deletions and information-theoretic arguments, requiring careful sharing of input among players. The algorithm builds upon prior works, including the dynamic streaming MIS algorithm of ACG plus 1.5, and the model-independent reduction of Veld 24, from vertex cover to randomized greedy MIS. The combination of these works implies a semistreaming algorithm for finding a 2 approximate vertex cover in dynamic streams. However, extending these ideas to matching is challenging, and the paper discusses the challenges and potential solutions. The proposed approach involves designing a new scheme for finding a fractional matching from a single run of the randomized greedy MIS algorithm. This scheme assigns a value of 1 deg v to every edge v w, with deg w is less than or equal to deg v whenever a vertex versus joins the vertex cover C. The assignment is designed such that the total x value incident on any vertex is not much more than 1, allowing for a rescaling to obtain a fractional matching. The key observation is that in each iteration of the algorithm, if the expected borrowed assignment by a vertex is high, then this vertex also has an equally high chance of being removed from consideration after this iteration. The expected borrowed assignment of a vertex W in an iteration is bounded by the probability of W being removed in that iteration, as shown in equation 3. This leads to a probabilistic question of upper bounding the total borrowed assignment of a vertex W over all iterations, subject to the condition that the expected loss in each step is upper bounded by the probability of terminating the experiment at that step. The analysis shows that the expected total borrowed assignment of a vertex W is bounded by a constant factor, and the variance is bounded by an O(1) factor of the expectation. Using Chebyshev's inequality, it can be shown that the expected overflow of the assignment X can be bounded, allowing for a fractional matching to be obtained by trimming down X by a constant factor. The resulting fractional matching is an O(1) approximation in expectation, as shown by the duality of matchings and vertex covers. The proposed approach provides a lightweight reduction for finding an O(1) approximate fractional matching in expectation from a single execution of the randomized greedy-Mies algorithm. The paper also discusses the development of a dynamic streaming algorithm for matchings, which is an extension of the semistreaming implementation by ACG+15. The main challenge lies in incorporating the reduction from fractional matchings to randomized greedy-Mies into this algorithm. The authors outline three key challenges: large support in fractional matchings, determining neighbors of a vertex joining the vertex cover, and determining which edges receive fractional matchings. To address these challenges, the authors propose several solutions. First, they use a standard trick to sample each edge of the graph independently with probability asymptotically equal z lane n, where z is the value of the edge in the fractional matching. This allows them to recover a large enough matching. Second, they augment the semistreaming algorithm to add a timestamp t, v, to each vertex versus that joins the vertex cover, which helps in identifying the set of its neighbors still present in the graph when versus joins the vertex cover. The authors also propose a method to compute these timestamps using the residual sparsity property of the randomized greedy-Mies. They partition each batch into O log n subbatches and prove that, with high probability, for every vertex V, the first subbatch containing at least one neighbor of V in E can only have log n neighbors of V in total. This property allows them to recover the timestamps of all vertices using O(1) passes and O(n) polylog n space. Finally, the authors delegate some computation of the fractional matching in the reduction to the analysis. They compute the timestamps and sample asymptotically equal log n deg v fraction of remaining neighbors of versus the total number of edges sampled. This way will be asymptotically equal n log n edges, and they can find them using a sparse recovery approach. The rest of the algorithm involves returning a maximum matching of these sampled edges and performing a simple rejection sampling idea to recover a subsampled version of the fractional matching X in the reduction. The authors establish a lower bound for dynamic streaming algorithms solving the maximum matching problem, utilizing the hierarchical embedding technique to prove an omega log n pass lower bound. This technique involves constructing a hard instance for PPASS streaming algorithms by embedding a collection of P1 pass hard instances inside a single graph. The algorithm must solve a special subset of these instances, hidden in the first pass, to find the maximum matching. The authors adapt this technique to prove a dynamic streaming lower bound, addressing challenges that arise in this adaptation. They borrow ideas from prior work to construct hard instances and analyze them using information theoretic tools. The lower bound relies heavily on communication complexity arguments, which are briefly overviewed. The hierarchical embedding technique constructs a graph G containing a collection of P1 pass hard instances, forcing the algorithm to solve a special subset without revealing their identity in the first pass. The authors prove that any algorithm must either spend omega AB space to learn non-trivial information about all subinstances or spend its first pass learning the identity of the special instances and then solve them independently in the remaining P1 passes. The authors discuss challenges in applying hierarchical embeddings for approximate matchings in dynamic streams, including combinatorial and information theoretic aspects. They address these challenges by borrowing ideas from previous works, such as using an idea due to DK20 for proving single-pass O1 approximation lower bounds for matchings in dynamic streams. This allows them to create an instance involving only one induced set of P1 pass instances. The authors also borrow ideas from AKZ24 for augmenting the input of players even for multi-round pass algorithms on dynamic streams, addressing information theoretic aspects of O1 approximate matchings. They discuss their fix to the first challenge, using a communication problem where Alice receives an n times n matrix A encoding the bipartite adjacency matrix of a random bipartite graph G. The input graph G at the end of the stream has an induced matching M of size n, 2O, n, with high probability and a vertex cover of size O, n. Any O1 approximate matching algorithm on the graph needs to recover many edges of M. The authors present a multi-pass lower bound construction for the augmented hidden matrices AHM problem, a two-player communication problem. The construction involves hierarchically embedding many instances of AHMR1 into a larger instance of AHMR, creating a hard instance. The embedding technique creates a graph G consisting of induced hard R1 round instances, defining edges to be inserted and deleted from the graph. The construction begins with a matrix A of R1 hard instances, where each instance is an AHMR1 problem on NR1 vertices. The matrix B is defined by picking two random permutations of the row groups and column groups of the matrix A and applying these permutations to the instance matrix I. The authors argue that the constructed instance of AHMR is hard because it contains a large induced subgraph consisting of vertex disjoint copies of hard R1 round instances. The authors analyze the parameters of the construction, showing that the communication space needed to solve the instance is at least min T2R, TR, SR1, NR1. They establish a lower bound on the number of rounds required by EO/N communication protocols for the approximate hypergraph matching AHM problem, implying that omega log n rounds are needed for AHMR and omega log n passes are needed for semistreaming algorithms for O1 approximation of matchings. The authors use information theoretic arguments to prove the hardness of their instances, revisiting the one-round lower bound of DK20, and providing a new proof that shows none of the diagonal entries of B can be revealed by Alice's message. They discuss the partitioning of the input, allowing Alice to insert all edges in B and Bob to delete all edges inserted by Alice in the off-diagonal instances, creating the inducedness property. The paper presents a multi-round lower bound for the all-or-nothing hidden matrix AHM problem, a fundamental problem in communication complexity. The authors employ a three-step approach, differing from previous work in the direct sum argument and compression technique used. Step 1 transforms an round protocol for AHMR to an round protocol for AHMR1 with reduced information cost, utilizing internal information cost direct sum arguments. Step 2 compresses the communication of the protocol using existing message compression arguments, specifically the technique of 16 Japanese yen. Step 3 eliminates one round, incurring an additive factor on error probability, resulting in an R1 round protocol for AHMR1. The authors establish that the resulting protocol succeeds with non-trivial probability, implying a lower bound of N1 plus half an ohm R communication for round protocols for AHMR. This, in turn, implies that any PPASS streaming algorithm for O1 approximation of matchings requires N1 plus half an ohm P space, with semistreaming algorithms requiring omega log n passes. The paper also explores the use of sparse recovery algorithms in graph sketching, introducing notation and definitions, including graph concepts and fractional matching. The authors discuss concentration inequalities, limited independence hash functions, and sparse recovery algorithms, providing a detailed description of their space complexity and probability of success. They note the application of sparse recovery algorithms in graph sketching, dating back to AGM12, and provide a comprehensive toolkit for practitioners, including algorithm descriptions, space complexity, and probability of success. The results have implications for graph sketching, enabling the recovery of sparse vectors from dynamic streams. The paper discusses various techniques for sketching and streaming tools in graphs, focusing on vertex sampling approaches to reduce the number of vertices while preserving the largest matching approximately. This method is crucial for finding matchings in dynamic streams in a single pass. The boosting framework is also discussed, which improves 0.1 approximation algorithms to 1 plus epsilon approximation algorithms in dynamic streams. In the context of two-party communication complexity, the paper establishes a connection between communication protocols and streaming algorithms, showing how a PPASSS space streaming algorithm can be translated into a two-party protocol with 2p1 rounds and OPS communication cost. Message compression techniques are presented to reduce the communication cost of limited round protocols close to their information cost. The paper also presents a randomized greedy algorithm for finding an approximate fractional matching in a graph by growing the random maximal independent set, MIS. This algorithm is the core of the approach and is provided in a model-independent manner. It can be implemented in dynamic graph streams as an log n pass semistreaming algorithm and improved to yield an approximation factor of 1 plus epsilon. The main properties of this algorithm are captured in Theorem 2. Which provides separate guarantees for the assignments x and y. Given any graph G and parameter beta less than 1/8, algorithm 1 outputs an integral vertex cover V-cover, an intermediate solution x element of Re, and a fractional matching y element of Re such that xe element of x beta, 2e, V-cover. This implies that the fractional matching y returned by the algorithm is a multiplicative approximation in terms of beta. The analysis of the algorithm's performance continues with the derivation of a lower bound for the expected value of the solution. Specifically, it is shown that for any choice of the random bits $r less than $t, the expected value of the solution $x is at least $beta, CDOT2, CDOTE, V, T, underscore, cover, r less than $t. This result is obtained by combining two equations, one of which relates the expected value of the solution to the expected value of the number of vertices in the cover, and the other of which relates the expected value of the number of vertices in the cover to the expected value of the solution. The proof of this result relies on the definition of the algorithm and the properties of the indicator function. Additional notation is introduced, including $x, t, underscore v $out, t, underscore v and $in, t, underscore v which represent the value of the edges incident to vertex $v at iteration $t. The value added to $x, t, underscore v by vertex $v itself, and the value added to $x, t, underscore v by other vertices, respectively. It is shown that $x, t, underscore v equals out, t, underscore v plus in, t, underscore v and that $out, t, underscore v is non-zero in at most one iteration. The analysis then focuses on bounding the value of $in, t, underscore v across the iterations. It is shown that the total sum that can be assigned to vertex $w across the iterations is upper bounded by beta in expectation. Furthermore, an upper bound on the expected value of $in, t, underscore w is derived, specifically $e, in, t, underscore w, r less than t, is less than or equal to beta, pr, e underscore w, t, r less than t, $. This result implies that if $in, t, underscore w is expected to be large, then there is a good chance that $w will be removed from $g, t, and no longer receive value in subsequent iterations. The authors also establish an upper bound on the value of $in, t, underscore w in any iteration $t, showing that $in, t, underscore w is less than or equal to beta $. This result is used to bound the variance of the total value assigned to $w, which is shown to be at most $3 beta, e, x underscore t is greater than or equal to 1 in, t, underscore w, $. A concentration inequality for the total value assigned to $w is then derived, specifically $pr x_t is greater than or equal to 1 in t_w greater than theta, is less than or equal to 3 beta theta beta squared x_t is greater than or equal to 1 in t_w dollar, where $theta is greater than or equal to 1 beta dollar. The paper presents a novel algorithm for the maximum independent set MIS problem in dynamic streaming graphs, combining the randomized greedy MIS algorithm with a new dynamic streaming implementation. The authors provide a detailed analysis of the algorithm's performance, including its approximation ratio and time complexity. The dynamic streaming implementation processes the graph in batches of vertices with growing sizes, using a key new subroutine to determine the timestamp of all vertices. This is achieved via algorithm 2, which finds the set V-cover in algorithm 1 and assigns a timestamp to each vertex. The analysis of algorithm 2 relies on a greedy approach and involves bounding the space complexity using a helper lemma, originally due to ACG plus 1.5. This lemma states that with high probability, the maximum degree of GI is bounded by 100 ni1 lane n . Claim 4.9 then bounds the space complexity of algorithm 2 to O n log squared n with high probability. Algorithm 3 is introduced to find the timestamps in line 2D of algorithm 2, partitioning the set UI into groups based on geometrically increasing sizes and using a randomized Q sparse recovery algorithm. Lemma 4.10 states that algorithm 3 finds the timestamps in line 2D of algorithm 2 with high probability and can be implemented in O n log cubed n space. The paper concludes by discussing the implications of the results and potential future directions for research, highlighting the suitability of the algorithm for large-scale dynamic graphs. Algorithm 3's correctness is established by demonstrating that it finds the required timestamp t, v, with high probability for any vertex v element of v_ms. The algorithm's performance is analyzed by considering the smallest index J-star operator element of b, where parallel phi v J-star operator parallel 0 greater than 0. If no such J-star operator exists, V is not a neighbor to any vertex in V_ms and will not be added to V-cover. Otherwise, the neighbor U of V in V_ms with the smallest value of t, U, belongs to UI, J-star operator, and returning such U is the correct answer. The algorithm's error sources are identified, including the randomized sparse recovery's potential failure to retrieve phi v j for all v in V_ms and j element of b. Using the union bound, it is shown that this event happens with probability at least 1-n-198 for the choice of delta equals n-200. Claim 4.11 is introduced to bound the probability that parallel phi v J-star operator parallel 0 greater than q. The claim states that for any j greater than 1 and any vertex v element of V_ms, if parallel phi v j-1 parallel 0 equals 0, then parallel phi v j parallel 0 less than slanted equal q with high probability. The proof involves defining useful notation, such as gi, j, dj, v, and key, j, and using Chernoff bounds to argue that with high probability, the sparsity of phi v j is at most q. The case when dj, v, 100 lane n, pj is also analyzed, and it is shown that dj, v, 25 ln n, pj-1 in all cases. This leads to the conclusion that j cannot be the first index with non-empty support in phi v j, and claim 4.11 is established. The proof is finalized by arguing that if j equals 1, UI, 1 has only 2 vertices and phi v 1 is too sparse. For any j greater than 1, claim 4.11 is used to argue that for any vertex v phi v J-star operator is q sparse with high probability. This proves the correctness of the algorithm. The space complexity of the algorithm is also analyzed, and it is shown that for every v element of V, O log 3n space is needed to maintain O lone randomized sparse recovery algorithms. This leads to a total space complexity of O(n)log3n. The reduction of algorithm 1 is used to recover a large matching from the input graph. The algorithm allows for the recovery of timestamps of all vertices in a single run of the randomized greedy Ms algorithm in O(log n) passes over a dynamic stream. The goal is to sample the edges of the graph with probabilities proportional to their y values and use the sampled edges to find a large matching. The authors aim to sample each edge of the graph with probability pay, but face the challenge of not being able to recover the values of y, or even x, explicitly and learn pays. To address this, they use a proxy for them algorithmically. They start by utilizing the time stamps of all vertices to find the degrees of all vertices at the time they are settled, as stated in observation 4.12. This observation allows them to assume they have the remaining degree of every vertex v at the time it is settled, fixing the value x will assign to the edges of verses. However, they still lack sufficient information to perform the check-in line 2c of algorithm 1 to know which incident edges of v receive a non-zero fractional matching. To sidestep this issue, they define an intermediate assignment z element of R(e), which can be explicitly found for any pair of vertices. The vector z is defined as zuv equals 200 log n, deg, t, vert, u, v, vert, u, v, where vert, u, v, is the vertex to which the pair, u, v, is assigned, as per definition 4.13. The authors then show the relevance of z values in claim 4.15, which states that for every edge E element of E, pay is less than or equal to z, where pay element of 0, 1, is from EQ, 14. This claim is proven by arguing that z is less than or equal to beta, deg, t, vert, e, where z is updated in at most one iteration of the loop in line 2c of algorithm 1. Given claim 4.15, the authors can sample the edges with probability proportional to z values, which can be computed. They propose a two-step sampling process. First, sample all pairs, u, v, based on their value zu, v to obtain a vector phi z element of R(v squared), and then maintain a sparse recovery algorithm over phi z to recover the actual edges inside this sample. The sampling is done using a kappa-wise independent hash function, where kappa equals 200 log n. The authors present a novel approach to finding a large matching in a graph, leveraging a combination of sampling and rejection sampling techniques. They define a set phi z of pairs, u, v, such that h, u, v, is less than or equal to min 1, zu, v, where h is a kappa-wise independent hash function and zu, v is a probability value. The incidence vector phi z of Ez, the intersection of E and phi z, is then obtained by sampling each edge E and E with probability z. The authors prove that the size of Ez can be bounded with high probability, specifically, Ez equals O(n) log n, using a combination of propositions 3.4 and 3.5. This is achieved by showing that the number of edges assigned to each vertex v, denoted by a, v, is O log n, with high probability. The authors then define an indicator random variable z for each edge E in a, v, which is 1 if E is sampled and as. By applying proposition 3.5, they bound the probability that the number of sampled edges in a, v, exceeds 400 log n. The authors then relate the sampled edges Ez to a fractional matching y obtained from algorithm 1. They define an alternative sampling process for obtaining a set EP, which is a subset of Ez. By rejecting edges with pay less than h, E, is less than or equal to z, they show that EP contains a fractional matching with expected size approximately equals y. This is achieved by defining an assignment y asterisk operator E for each edge E in E, which is supported only on the edges in EP. The authors then prove that y asterisk operator can be scaled to become a fractional matching, implying that EP contains a fractional matching with expected size approximately equals y. The authors conclude that the expected size of the matching in Ez is at least 1,8 beta, 1,2 beta, beta, 10, micro, g, where micro, g, is the size of the maximum matching in G. This result is obtained by applying the law of total expectation and leveraging the correctness probability of algorithm 2. In the context of machine learning and computer science, the paper discusses a novel approach to solving the maximum matching problem in a graph. The authors propose an algorithm that uses a combination of vertex sampling and sparse recovery techniques to achieve a high probability bound on the approximation ratio of the algorithm. The paper begins by defining a fractional matching and its relationship with the maximum matching problem. It then introduces the concept of a dynamic streaming algorithm, which is used to solve the maximum matching problem in a graph. The authors provide a detailed analysis of the algorithm's performance, including its space complexity and approximation ratio. The authors also discuss how to boost the probability of success of the algorithm to a high probability bound. This is achieved by using the vertex sampling approach of proposition 3.7 for O, log n, guesses of micro g, as powers of 2 between log 2, n, to n and running the algorithm for each guess separately in parallel. In conclusion, the paper presents a new approach to solving the maximum matching problem in a graph using a combination of vertex sampling and sparse recovery techniques. The proposed algorithm achieves a high probability bound on the approximation ratio, making it a significant contribution to the field of machine learning and computer science. The paper presents a novel algorithm for finding a maximum matching in a graph using a dynamic stream, operating in the semistreaming model with limited memory. The algorithm samples a subset of vertices, finds a matching within this subset, and repeats the process to approximate the maximum matching. With high probability, the algorithm achieves a matching at least half the size of the maximum matching. A lower bound on the number of passes required by any semistreaming algorithm to approximate the maximum matching problem is established through a connection between the streaming and communication models, using the augmented hidden matrices (AHM) problem. The authors prove that any round protocol solving AHM with a certain probability of success must have a communication cost of at least a specific value. This result is then used to construct graph instances corresponding to the AHM problem, showing a connection between any PPASS dynamic streaming algorithm for approximate maximum matching in AHM, where R equals 2p1. The paper also discusses the lower bound on the space complexity for computing in O(1) approximate maximum matching in a graph, using the AHM problem. Any dynamic streaming algorithm using n polylog n space to compute an O(1) approximate maximum matching must use at least log n passes. The AHM problem is defined recursively, involving a matrix input for Alice and a bit input for Bob, with a series of messages exchanged between the two players. The paper establishes a fundamental limit on the efficiency of algorithms in the semistreaming model for solving the maximum matching problem, showing that any semistreaming algorithm must use at least log n passes. The AHM problem is further explained in detail, including the base case and recursive instances, with special subinstances and off-diagonal subinstances defined. The search sequences used to identify the solution to the AHM instance are also described. Overall, the paper provides a crucial bound on the space complexity for computing an O(1) approximate maximum matching in a graph using the AHM problem. The paper discusses the augmented hidden matrix (AHM) problem, a fundamental issue in communication complexity. It presents a novel approach to solve the AHM problem using a recursive construction method. The authors define the AHM problem and its parameters, including the number of rounds, R, the size of the matrix, N, and the asymmetry parameter, alpha. They also introduce a hard distribution doctor, NR, alpha, for the AHM problem, which is crucial for the analysis of the communication complexity. The authors then prove a lower bound on the communication complexity of the AHM problem. They use a round elimination argument to show that if there exists a deterministic protocol for AHMR with low communication complexity, then there must be a deterministic protocol for AHMR1 with even lower communication complexity. This process is repeated until they reach the base case of AHM0, where they can use an observation to contradict the assumption of a low communication protocol. The paper also includes a detailed explanation of the parameters and the hard distribution used in the AHM problem. The authors provide an illustration of the AHM problem and explain how the search sequence is defined. They also discuss the limitations and future work related to the AHM problem. In summary, the paper presents a novel approach to solve the AHM problem using a recursive construction method and proves a lower bound on the communication complexity of the AHM problem. The authors provide a detailed explanation of the parameters, the hard distribution, and the limitations of the AHM problem, making this paper a significant contribution to the field of communication complexity. The paper discusses the communication complexity of the approximate Hamming distance problem, AHM, in the multi-party number and hand model. A round elimination argument is presented to show that any deterministic round protocol for AHM with a certain communication cost and success probability can be transformed into a deterministic, R1, round protocol with a slightly higher communication cost and a slightly lower success probability. The authors bound the communication cost of a deterministic protocol pi R1 constructed from pi R using equation 20, and simplify the term SR 2b2R alpha 2 in equation 22 to obtain a bound on the probability of success for pi R1. This bound is used to show that the deterministic protocol pi R1 contradicts the lemma for R1, thus proving the lemma for deterministic round protocols when the input is sampled from the distribution doctor for every R is greater than or equal to 1. The round elimination argument consists of 3 steps: input embedding, message compression, and guessing the first message. In the input embedding step, a randomized round protocol pi 1 R is constructed with a success probability similar to pi R and an internal information cost less than the communication cost of pi R by a KR multiplicative factor. In the message compression step, a randomized round protocol pi 2 R is constructed with a success probability less than that of pi 1 R by at most an additive epsilon factor and a communication cost similar to the internal information cost of pi 1 R under Dr. 1. The protocol pi 1 R is an round protocol for the augmented hidden matching AHM problem, which involves 2 players, Alice and Bob, who take on the roles of players PX and PY in the simulated input instance of AHMR. The protocol uses public randomness to sample a uniform random search index K-star operator and jointly sample variables from the distribution doctor, NR, alpha. Observation 5.7 states that in protocol pi 1 R, A, R, B, R, is sampled from doctor, NR, alpha, and K-star operator, K-star operator R-1, K-star operator R-2, K-star operator 0, is a uniform random search sequence. Claim 5.8 proves that the internal information cost of pi 1 R about its input sampled from doctor -1 is 1 kr times smaller than the information cost of pi R about its own input sampled from doctor. Here is a combined summary of the 4 pages. The authors continue to analyze the protocol pi 1 R, bounding the mutual information terms and establishing an upper bound on the internal information cost. They introduce lemma 5.9, which states that pi 1 R is an round protocol for AHMR-1, NR-1, alpha, with communication cost at most S, probability of success at least delta, and internal information cost at most S, KR. The authors then describe a low communication cost protocol pi 2 R, obtained by compressing the communication cost of pi 1 R using standard message compression techniques. The communication cost of pi 2 R is upper bounded by CJP, R, epsilon, S, KR plus R, and the probability of success is at least delta minus epsilon. The protocol pi 2 R is constructed by adding an independent source of public randomness to pi 1 R, compressing the messages sent in pi 1 R. The authors then eliminate the first message by making the players guess it using public randomness, altering the joint distribution of the input and affecting the guarantees of the protocol. The R1 round protocol pi R1 for AHMR1 is constructed by embedding the input for AHMR1 into a simulated instance of AHMR. The players simulate a run of pi 2 R using the simulated instance, where the first message is guessed using public randomness. The joint distribution of the input and first message in pi r1, denoted as dfake, is compared to the joint distribution in pi 2 r, denoted as dreal. The authors show that the two distributions only differ in the way that the input, A star operator, B star operator, is sampled. By bounding the mutual information terms, they prove that the corresponding terms in dreal are identical to those in dfake. The construction of the protocol pi r1 and the comparison of the distributions dfake and dreal establish the guarantees of the protocol, showing that pi r1 is a valid, r1, round protocol for a HMR1 with similar guarantees to pi 2 r. The paper presents a comprehensive information theoretic analysis of a specific quantum communication protocol, focusing on the mutual information between different components of the system. It begins by establishing a chain rule for mutual information, which is used to bound the mutual information between two sets of variables in the protocol. This bound is crucial for understanding the flow of information within the system and how it affects the overall performance of the quantum communication protocol. The authors then delve into the specifics of the quantum communication protocol, introducing concepts such as simulated instances, real instances, and fake instances. They provide a detailed explanation of how these instances are generated and their roles in the protocol. The main goal is to show that the total variation distance between real and fake instances is small, which implies that the protocol can efficiently simulate quantum communication without revealing too much information about the input. To achieve this, the authors use various claims and lemmas to bound the mutual information between different variables in the system. For example, Claim 5.12 shows that certain variables are independent given specific conditions, while Claim 5.13 provides a bound on the mutual information between a variable and a set of messages. These bounds are essential for establishing the desired properties of the quantum communication protocol. The paper also introduces partial definitions of permutations, such as tro and tcol, which represent ordered sets of rows and columns in a matrix. These definitions are used to further bound the mutual information and demonstrate the efficiency of the protocol. The authors provide an illustration of these definitions in Figure 10, which helps to visualize the relationships between different components of the system. Claims 5.14 and 5.15 are crucial in bounding the mutual information between certain random variables. Claim 5.14 states that the distribution of bspec_k is independent of the permutations rho r and rho c conditioned on tro tcol rho r br alpha plus k and rho c br alpha plus k . Using this claim, the authors bound the mutual information I, bspec_k, pi 1, sigma r, sigma c, z, by conditioning on z, tro, tcol, rho r, br alpha plus k, and rho c, br alpha plus k, . They then apply the definition of conditional mutual information and the linearity of expectation to obtain an upper bound on the mutual information. Claim 5.15 states that the information revealed by random variable raw about the input A star operator, B star operator, is not too large and dreal . The authors prove this claim by showing that I, aspec_k star operator, bspec_k star operator, raw equals I, bspec_k star operator, raw plus I, aspec_k star operator, raw bspec_k star operator, where the second term is 0. They then bound I, bspec_k star operator, raw using the chain rule of mutual information and non-negativity of mutual information. The authors use these claims to establish an upper bound on the mutual information between certain random variables, which is crucial in their analysis. The technical details of the proofs, including the use of conditional mutual information, linearity of expectation, and chain rule of mutual information, demonstrate the author's rigorous approach to bounding the mutual information. The paper discusses the augmented hidden matrices, AHM, problem, a fundamental issue in communication complexity. It involves two players, Alice and Bob, who are given matrices A and B, respectively, and a search sequence. Their goal is to determine if the search sequence is in the intersection of A and B without revealing any additional information about their matrices. The authors present a round elimination argument for the AHM problem, reducing the number of rounds in the communication protocol while maintaining the probability of success and controlling the communication cost. This is achieved by using a combination of techniques, including the chain rule for mutual information, Pinsker's inequality, and Jensen's inequality. The paper also establishes a connection between the AHM problem and the maximum bipartite matching problem in the dynamic streaming model. It shows that any PPASSS space dynamic streaming algorithm that computes a beta approximate maximum matching on a bipartite graph can be used to construct an round protocol for AHMR with a non-trivial probability of success and controlled communication cost. Furthermore, the paper discusses the construction of a bipartite graph using the alternating Hamiltonian matrix (AHM) model, specifically focusing on the AHMR model. This model is defined recursively, with each instance comprising B(R) many AHMR1 subinstances. Each of these subinstances has its own K(R1) many special subsubinstances, ultimately corresponding to the K(R)K(R1) K(1) many special base instances, where each one corresponds to a single bit. The base instances or bits are represented in the graph using a basic bipartite graph construction called a big graph. This graph has 4 vertices and encodes bits in the construction of G. The bit x can be identified by either of the edges in E. Given an instance, A, R, B, R, of AHMR, N_R, alpha, the paper provides a recursive procedure that separately encodes A, R, and B, R, as the edges of a bipartite graph on the vertex sets L and R. For ease of notation, L, I, and R, J, are defined as subsets of L and R, respectively, for I, J element of B(R). The edges added corresponding to the subinstance, A, R1, I, J, B, R1, I, J, will be only across vertices in L, I, and R, J. The construction of the graph is as follows. For R equals 0, when Z element of 0, 1, return the edges of the big graph corresponding to Z for R is greater than or equal to 1. When Z element of 1, N_R, 0, N_R, return the edges I, J element of B(R), edges R1, Z, L, I, R, J, where Z is the N_R1 times N_R1 matrix with all its entries the same as the entries in Z. When Z equals A, R, return the edges I, J element of B(R), edges R1, B, R1, I, J, L, I, R, J. When Z equals B, R, return the edges I, J element of B(R), B(R) alpha less than sigma_R, I, does not equal sigma_C, J, is less than or equal to B(R) edges, R1, B, R1, I, J, L, I, R, J, union, I, J element of B(R), B(R) alpha less than sigma_R, I, equals sigma_C, J, is less than or equal to B(R) edges, R1, A, R1, I, J, L, I, R, J. If R is even, in addition to the above, return the edges I, J element of B(R), sigma_R, I, is less than or equal to B(R) alpha or sigma_C, J, is less than or equal to B(R) alpha edges, 0, 1, N_R1, L, I, R, J, union edges, 0, 0, N_R1, L, I, R, J. The paper also claims that for any R is greater than or equal to 0, given an instance, A, R, B, R, of AHMR, N_R, alpha, Alice and Bob can compute edges, R, A, R, L, R, and edges, R, B, R, L, R, respectively, without any communication. The proof of the claim is by induction on R, where the base case when R equals 0 is trivial. For any R is greater than or equal to 1, the player holding A, R, has access to all B, R1, underscore, I, J, for I, J element of B caret R. Thus, the player can construct the required set of edges R1, B, R1, underscore, I, J, L, I, R, J, for all I, J element of B caret R, without any communication. The construction of a bipartite graph G from an instance A, R, B, R, of the asymmetric hypercube matching AHM problem is presented. The graph G is constructed recursively, with one player inserting edges and the other player deleting edges, depending on the parity of R. The recursive definition of the graph construction is presented, where the player holding B, R, has access to permutations sigma R and sigma C, allowing them to construct the required edges without communication. The main procedure for constructing the graph G is presented, where one player inserts edges and the other player deletes edges. The roles of Alice and Bob depend on the parity of R. When R is odd, Alice inserts the edges and Bob deletes the edges, and when R is even, the roles are reversed. The constructed graph G is a valid graph, namely, a del subset equal 1, as proven by induction on R. In the context of the alternating Hamiltonian model, AHM, two different groupings of edges are considered. For even R, three cases are analyzed, showing that a del subset equal 1 for any choice of R is greater than or equal to 0. The players can take an instance, A, R, B, R, of AHM and construct a valid graph G without any communication. Special vertices L-spec and R-spec are defined, and it is shown that they correspond to the special subinstances, A-spec, B-spec, of A, R, B, R. The subgraph of G induced by the vertices L-spec union R-spec is exactly the vertex disjoint union of graphs graph, A-spec, B-spec, for all K element of Kr. Special base instances and their corresponding sets of special base vertices are identified, and it is shown that the special base vertices L union R correspond to the special base instances A, B, using claim 5.20. Here is a combined summary of the 4 pages. The alternating Hamiltonian matching AHM problem is addressed through a graph construction utilizing a bipartite graph G equals graph A, R, B, R. To simulate a run of any PPASSS space dynamic streaming algorithm A for a beta approximate maximum matching. The graph construction is based on special base instances and their corresponding bit graphs, which identify the bits of these instances in G. Key properties of this construction include the vertex disjoint union of subgraphs H-spec, each corresponding to a special base instance, and the identification of bits of at least nr 1, beta minus 2 alpha r, many special base instances in A, R, B, R. A protocol pi is presented for solving the AHM problem using a dynamic streaming algorithm. The protocol involves simulating each pass of A on the stream of insertions sigma followed by deletions sigma B, while exchanging messages to identify the labels of special base instances in A** operator, B** operator. The protocol consists of 4 steps: computing edge insertions and deletions, simulating each pass of A, identifying special base instances, and returning the output of the protocol. The protocol requires R rounds of communication, where R equals 2p1, and has a communication cost of cc, pi, is less than or equal to rs plus O, R squared nr log nr. The probability of success is suc, pi, is greater than or equal to 1/2 plus 1, 6 beta, where beta is the approximation guarantee of the maximum matching returned by A. The protocol is used to prove the connection between maximum bipartite matching in the dynamic streaming model and the AHMR problem. The analysis of the protocol's communication cost involves bounding the number of bits sent in each round, resulting in a total of O, RNR log NR, bits sent in R rounds. The probability of success is analyzed by considering the case where A succeeds in outputting a beta approximate maximum matching M, which identifies the bits of at least NR 1, beta 2 alpha R, many special base instances. The protocol's success probability is analyzed across 3 scenarios, yielding a probability of at least 1/2, 1 plus 1/3 beta, where beta is a constant. This probability is derived from the cases where algorithm A succeeds and algorithm M correctly identifies the solution bit, when A succeeds but M fails, and when A fails. The construction of graph A, R, B, R is also discussed, highlighting the difference in behavior when R is even versus odd. Specifically, when R is odd, the construction adheres to the restriction of dynamic graph streams, whereas when R is even, it does not. The authors engage with the broader research community through a comprehensive list of references, citing works from various conferences and journals, including SOTA, ICML, STOC, and Approximately, Random. These references cover topics such as semistreaming maximum matching, multipass graph streaming lower bounds, and polynomial pass semistreaming lower bounds for K-cores and degeneracy. The paper discusses various algorithms and techniques for solving graph problems in streaming models, focusing on dynamic graph streams and the simultaneous communication model. Algorithms for maximum matching in vertex cover problems are presented, including a single-pass semistreaming algorithm for delta coloring and a multipass algorithm for finding a maximal independent set. Lower bounds for these problems are also discussed, showing that certain algorithms are optimal in terms of the number of passes required. The authors explore kernelization via sampling for finding matchings and related problems in dynamic graph streams, reducing the input graph size while preserving the solution. Parameterized streaming algorithms for solving vertex ordering problems in directed graph streams are also examined. Recent advances in superconstant pass streaming lower bounds for reachability and near-optimal 2-pass streaming algorithms for sampling random walks over directed graphs are covered, demonstrating ongoing research efforts to improve algorithm efficiency and accuracy. The paper delves into the challenges of approximating maximum bipartite matching in the streaming model, where edges arrive one at a time and cannot be revisited. It provides a comprehensive overview of previous work on this problem, including algorithms and lower bounds for both 1-pass and 2-pass streaming models. The authors highlight the importance of understanding the trade-offs between the number of passes and the approximation ratio achieved by algorithms in this context. They present new results on 2-pass streaming algorithms for maximum bipartite matching, including an unconditional lower bound for any 2-pass algorithm. This lower bound is based on a novel reduction from a communication complexity problem, demonstrating the power of this framework in understanding the limitations of streaming algorithms. The paper also discusses various algorithms and techniques for solving graph problems, particularly focusing on the semistreaming model. It introduces the concept of a simple augmentation method for matchings, which has applications to streaming algorithms, and explores filtering, a method for solving graph problems in MapReduce, and its implications for parallelism in algorithms and architectures. Furthermore, the authors discuss unconditional pseudorandom generators for low-degree polynomials and their relevance to matching theory, as well as optimal lower bounds for distributed and streaming spanning forest computation, and randomized distributed edge coloring via an extension of the Chernoff-Hofding bounds. The paper concludes with deterministic algorithms for maximum matching on general graphs in the semistreaming model and the growth of a random maximal independent set, which produces a 2-approximate vertex cover. Throughout the paper, the authors provide a comprehensive overview of the current state of research in these areas, highlighting novel ideas, significant findings, and important arguments. This section provides a comprehensive background on information theory, introducing essential definitions and facts necessary for the thesis. The Shannon entropy of a random variable A is defined as H, A, equals underscore, a element of sup, A. PR, A equals A, log 1, PR, A equals A, measuring the uncertainty or randomness of a conditional entropy and mutual information are also defined, with several useful properties presented, including non-negativity of entropy and the data processing inequality. 2 propositions describe the effect of conditioning on mutual information, stating that conditioning on a variable does not increase or decrease mutual information under certain independence conditions. The section also introduces the Kullback-Leibler KL, divergence and total variation distance as measures of distance between distributions. The KL divergence is defined as d mu nu equals e underscore a tilde operator mu log mu a nu a, measuring the difference between two distributions. The total variation distance is defined as parallel mn underscore tvd equals max underscore omega subset equal omega mu omega nu omega, representing the maximum difference between probabilities assigned by mu and nu to any event. Facts 8.6 and 8.7 provide crucial insights into the behavior of total variation distance under conditioning and its relationship with KL divergence. Fact 8.6 states that the total variation distance between distributions is bounded by the sum of the total variation distances of their conditional distributions. Fact 8.7, or Pinsker's inequality, bounds the total variation distance between two distributions based on their KL divergence. These facts have significant implications for machine learning, information theory, and statistical inference, enabling researchers to analyze and compare probability distributions more effectively. By leveraging these facts, researchers can assess the similarity between models, determine the convergence of algorithms, and construct tests for hypotheses involving distribution equality.